Okay, so we're going to integrate square root of cotangent x. Now, trying to integrate this function here, we've got a couple of problems. We've got the radical here and a trig function on its own. So we're going to need some sort of u substitution and trig identities to try and help us. So let's have a look at cotangent x first. So cotangent of x, we know this is basically the reciprocal of the tangent function. So that's 1 over tangent x. Now, if you put that in the square root, then we can put this in the square root. So that would take care of that, and then we can put this one all in the square root. And then this would just simplify to 1 over square root tangent x. Now, if we take the derivative of tangent x, looking at a u substitution, we get secant squared x. So that's kind of what we're looking to try and get some sort of relationship with this. So if we let our u equal tangent x, we'll have to try and do something with this secant squared x, with tangent x. Well, we know there's a trig identity, secant squared x equals tangent squared x plus 1. So I think that's the way we can go here to try and get something sorted out inside this integral here. So let's do a u substitution and let u equal tangent x. So bring it up on this board. U equals tangent x. So derivative on both sides, we get secant squared x dx. And then get the dx on its own. Dx equals du over secant squared x. So that's our first substitution. So let's go with that in our integral. So now we've got the integral. Cotangent x is basically 1 over the square root of tangent x. So 1 over square root. Tangent x is our u, so that takes care of that. And now we need to put in our dx, which is du over secant squared x. So we've got our du. Now secant squared x, we've got tangent squared x plus 1. Well, tangent squared x will be just u squared. So this will equal u squared plus 1. So let's put that in the denominator for our secant squared. So u squared plus 1, that takes care of that. So now we've just got a little awkward thing now with this radical here with the square root of u. So we can take care of that by just doing another substitution, just with making another one equal square root of u. So let's use the letter v. So if v equals square root of u, we take the derivative of both sides, then we get dv equals 1 over 2 times square root of u du, and then my du, which I need to get on its own, is just 2 times square root of u dv. Now square root of u, we know that is just our v. So we can take this completely into the v world. So 1 over square root of u, that's my v. My du is 2 square root of u dv, with square root of u being v, so that's 2v dv. So 2v dv. And then u squared plus 1. Well, v equals the square root of u, so let's go through this. V equals square root of u, so therefore v squared equals u. And as we want u squared, we can go v to the 4 equals u squared. So that we can put in for our u squared. So now we've got v to the 4, and then the plus 1, that stays. Okay, so now we can do some cancelling out. So these v's cancel out. The 2 can come out the front. So we can rewrite this integral as 1 over v to the 4 plus 1 dv. So let's take care of that. Okay, so v to the 4 plus 1 in our denominator. Well, this is partial fraction decomposition. That's the way forward on this. Well, if you check the link below, we did this partial fraction yesterday with this video in mind. So to save time on this integral, I'm going to just show you the result that we got yesterday for this. So just concentrating on that. So you can check the link to see how that's worked, but I'm just going to plug in the value here that we got yesterday and then we can continue with the integral. So we got, let's put this over here, 2 times, and the partial fraction decomposition was v plus root 2 over square root of 8 times quadratic, which was v squared plus root 2v plus 1. So that takes care of the first part. And the second part was subtract v minus root 2, and then square root of 8 again, and then quadratic here, but with a minus sign. So v squared minus root 2v plus 1. And then if I just take this off the board here, I can get my dv in. So just right here, dv. Okay, so that's where we got to. So now what we want to try and do something here now to try and integrate this straight off. Well, I can see here I've got this denominator. If I take the derivative of it, I'm almost the same as my numerator, and the same here on this one. And then what that would give us is just the logarithm of this denominator here. But I haven't quite got there because the derivative of this is 2v plus root 2, and I've got v plus root 2. So v plus root 2, I could perhaps write that a little bit different. So if I've got v plus root 2, if I want to get a 2v here, I could just write a 2v there, but I've changed the value. So now what I'll do is multiply it by a half. So then that would still be a v, but now I've only got a half of a root 2. So now I need to add another one at the end without this constant here. So I could add on 1 over root 2. That would then give us the same value in here. And the same with this one would apply if I just change this to a minus sign. So I'd have 1/2 of 2v minus root 2, which then I'd only have minus a half of this root 2. But then I would then have to add on another minus 1 over root 2. So I then have minus 1 over root 2. That way then I'd have my full square root of 2 in there. Okay, so let's rewrite that. Take the square root of 8 out as well, because that's on both, so I can bring this out the front here. So let's rewrite my integral here. So I've got 2 over this square root of 8. That takes care of that. Then v plus root 2, I'm just going to write this as 1/2 of 2v plus root 2. So that takes care of that. And then add on one more root 2. So 1 over root 2. And then I'm just going to write my quadratic here now in the denominator. So I'm now left with v squared plus root 2v plus 1. And then I'd have to do the same with this one. So now I've got minus half of this one, so half of 2v minus root 2, and then minus 1 over root 2, and then my denominator would be just this quadratic because the square root of 8 I've just taken out front. So I can now just divide all this by v squared minus root 2v plus 1, and then my dv. Okay, so now I've got my derivative in my numerator, which is great, so I've got a chance of getting a natural logarithm here. But I've got this 1/2 multiplied by this, but I've also got this one here also getting in the way. So what I can do now is split the fraction with this one, and I reckon I could do the same with this one. So my derivative is here of this one, and I've got this one here 1 over root 2, which I can then split the fraction here as well. So let's do that. So let's split the fraction into 2 fractions. So that one and that one, that one and that one. Okay, so let's bring this up the top with those fractions split. So let's do that. Okay, so now I've got this one up here. Now you'll see I've rearranged it with the 1 over root 2 of this one with 1 over root 2 here. So that takes care of that. I've left this one like this for now. And then this one, I've got minus 1/2 of this one, which is here. And you notice here I've put a plus sign with a 1 over root 2 because I've got a minus and a minus here, so that will give me a plus. So now let's just take this off the board. Okay, now let's just try and clean this up a little bit more. So now with these ones here, this one and this one in particular, I'm almost ready to integrate. So now what I'm going to do is I'm going to split my integral up a little bit now. So I've got a 1/2 here. So this 1/2 I can bring out the front with regards to this integral. So I'll have 2 over square root of 8. And then my 1/2 I can bring out here. So I can bring that to there. So obviously they're going to cancel out. And then I've got my integral, as we wanted, 2v plus root 2 over v squared plus root 2v plus 1. So that takes care of that one. And now this one, which is also looking good for my natural logarithm, I've got my constant here of 1/2 multiplied, which can be the same as this one. Enclose it all in this one integral. Then all I've got to do now is write this one here. So I've got minus 2v minus root 2, and then v squared plus root 2v plus 1, and then just dv. And then these ones here, I can just combine my root 2 here and bring that out with this one. So then I'm going to have separate integral 2 over root 8, and then because I've got a root 2 in my denominator, I just multiply this by root 2. So I'm just going to show that there, and then we can simplify that up in a minute. And then I've got my integral of this one and this one here. So I've got 1 over v squared plus root 2v plus 1. So let's put that one like that. Then add this one here. So add that to 1 over v squared minus root 2v plus 1. And then that one there is also dv. So now we've got two integrals here with slightly different constants out front. So let's cancel those ones out. And then I've got square root of 8, square root of 2, that's square root of 16, which is 4. 2 divided by 4, that now becomes 1/2. So let's just change that to 1/2 before we go any further with that one. And then don't forget my plus sign there. Okay, well, here we're ready to integrate because we've got our derivative in the numerators on both of them. So that's good. And then this one here, we're almost there with v squared plus 1 and v squared plus 1 with just an awkward root 2v plus and minus inside. So this one, we'll deal with that one in a minute. So let's integrate straight off. So 1 over square root of 8, and then the result of that is just the natural log of this denominator and the natural log of this denominator. So let's put that in there. So natural log, absolute value, v squared plus root 2v plus 1, and then subtract the natural log of this one. Natural log, absolute value, v squared. This one here is actually a minus sign, so let's just put that as a minus sign. It's v squared minus root 2v plus 1. So that takes care of that with a 1 over root 8 and all in brackets. So that's integrated. That's part of our answer now. Okay, now here we've got this one here. So v squared plus root 2v plus 1. Now let's take the square of our denominator and maybe that will lead us to the inverse tangent. So we've got plus 1/2 of the integral of 1 over. Now running through this to take the square, we've got v squared plus root 2 over 2. Root 2 over 2 we know is 1 over root 2. So we can write that as v plus 1 over root 2. Square that. And then we need to subtract this constant here squared. So that's minus 1/2. And minus 1/2 plus 1 gives us plus 1/2. And We'll have the same on this one, except we'll have a minus sign there, so that will take care of that. So we've got 1 over v minus 1 over root 2. Squaring that will still give us a positive 1/2, which we need to subtract, which will still be plus 1/2. So that's plus 1/2, and then that is also dv. Okay, so you can see this integral here. Be careful with minus signs here and there, it's really important. We had this one here which we could have left as a minus, and luckily I spotted this one from this one because we got the plus here. Very easy to get confused. Okay, so part of our answer, and now we're looking almost at the inverse tangent here, but we got this v plus 1 over root 2. So let's just have a look at that when we square it. So v plus 1 over root 2 squared. Now let's see what happens when we square that, and that might lead us to a substitution we can put in there, and also for this one. So if you square this, we'll have v squared plus, so 2 of these will be 2 over root 2. So that's basically 2 over root 2 just gives us root 2. So root 2 times our v, and then square that, we just get a half. So that takes care of that one expanded out. And then this one, so this is for this one, and for this one we'll have the same again but with a minus sign here. So I'm just going to put my working out for this one here as well, because that's going to help us get to our answer. So we've got a plus 1/2 here from this and plus 1/2 there, so that will lead us to a plus 1. But we've got this v squared plus root 2v. So why don't we let our use substitution be root 2v plus 1. So let's do that. So let w equal root 2v plus 1. And then somehow, because that's inside that, if we square this, we might get something with this. So let's square that. So w squared, so squaring this, we'll have 2v squared, 2 root 2v, 2 root 2v, and then plus 1. Okay, so we're almost the same as what we've got here. So if we do this over 2, do this over 2, we'll have this one and this one cancel with this one, and then this one will just become 1/2. So we'll have v squared plus root 2v plus 1/2, which is exactly what we want. So let's do another substitution. W equals root 2v plus 1. So let's put that one in. W equals root 2v plus 1. So we have to take the derivative of both sides. So dw is just square root of 2, and then that's dv. So get dv on its own. So dv equals dw over root 2. Okay, so this side here, we're going to have almost the same, but we can't use a w because I want to try and keep it in the same integrand. So we just change this one to another variable of t. So we'll split the integral up, and we'll let this time t equal root 2v, and instead of plus 1, because we've got a minus here, we'll have minus 1. And then if we square that, we'll have t squared equals 2v squared minus 2 root 2v, and then square that one, we'll have plus 1. So again, dividing by 2, and then cancelling them all out. This one and this one will cancel out, and then this one will make this a half. So it's exactly what we wanted when expanding on these terms inside. So again, our substitution this time will be t equals root 2v minus 1. So let's do that one as well. So t equals root 2v minus 1. So therefore dt equals square root of 2 dv, and then dv equals dt over square root of 2. So that's going to be our substitutions for these. So let's take these off the board and let's just continue down here. Okay, so now let's take care of our integral here. So now we're going to split this into two integrals. So let's give ourselves a little bit of space because this bit here is finished. So we've got 1/2, and then we've got the integral 1 over. So we had this one here, we worked this one out for v plus, so root 2v plus 1 for this v plus 1 over root 2. That was going to be w squared over 2. And then all we're left here now is just plus 1/2. So that takes care of that one. And then here we've got root 2 dw. So that's what our dv becomes. So dv, that becomes dw. And then square root of 2 we bring out here. So instead of 2 times square root of 2, I'm just going to write that as square root of 8. So that takes care of that one. And now let's transfer this one into our t. So now we've got plus. So same again, we'll have dt over root 2. So the constant for this one with that one will be again 1 over root 8. So that takes care of that. And then we'll have 1 over t squared over 2 plus 1 over 2. And then that will be dt. Okay, so this one here and this one here, we're almost there for the inverse tangent. We've got w squared plus 1, well they're both divided by 2. Same with this one, divided by 2. So if we factor out the 1/2 and do that like that, and the same again, factor out 1/2, we can then cancel out these denominators of divided by 2. So then we're just left with w squared plus 1 in there, and the same here, we'll just be left with t squared plus 1 in there. So now this 1/2, we then need to take this out. So as that's in our denominator, we can then flip that and just multiply everything by 2. So then we'll have 2 over the square root of 8. So now let's just rewrite that as 2 over square root of 8, and the integral of 1 over w squared plus 1 dw plus 2 over square root of 8, the integral again, because that one is the same as this one, that's why we've got the same constant. Then we've got 1 over t squared plus 1 dt. Okay, so we're almost ready to go straight into the integration here. So w squared plus 1, that'll be inverse tangent of w, and this one here will be the inverse tangent of t. Now all we need to think about now is 2 over square root of 8. Well, 2 over square root of 8 is, if I just write that like that, that equals 2 over 2 root 2. So basically these will cancel out to give us just 1 over root 2. So 1 over root 2. So then I could just change these constants to 1 over root 2. Okay, so now I'm going to take this off the board here up to this point, and I'm ready to write my answer. Okay, so now I've integrated this and I've put my result on a new line here with my inverse tangents, with this integral taken care of. So now we can take this off the board. So our answer is almost there. So now what we need to do now is do backward substitution and get our v back into our x, our w back to x, and our t back to x. Well, what is v? V is the square root of u, and u is tangent x. So that equals tangent x. So that takes care of that. Now what's our w? So w is root 2 v plus 1. So now w is root 2. V we know is square root of tangent x. And we need to remember the plus 1, very important. Okay, now what about our t? So let's bring the t over here. So t is root 2v minus 1. So basically it's the same as this with the minus 1 here. So we've got root 2 root tan x and then minus 1. So now we're ready to put our answer in here. So now we've got So this 1 over root 8, I'm going to write this as one big fraction. So I've got natural log, absolute value, v squared. Well, if v is square root of tangent x, v squared is just tangent x. So tangent x plus root 2 square root of tangent x plus 1. So that's my first one. And now my second one is the same again, but with a minus sign inside. So let's just take that. So minus natural log absolute value of tangent x minus root 2 square root of tangent x, and then that's going to be a plus 1 again. And then let's not forget that this is one fraction all over square root of 8. So let's just write that as 2 root 2. Okay, so that takes care of that. So now let's do my tangent and my inverse tangent. So remember, we've got root 2 tan x plus 1 and root 2 tan x minus 1. So let's just do that. So now I've got plus 1 over root 2. So I'm going to write another fraction down here as if I'm continuing. So continue my fraction here, all over square root of 2. So I'm going to put my square root of 2 in my denominator, and the inverse tangent of w. So remember, that one was all in brackets root 2 root tan x plus 1, and then the other one was the same again but with a minus sign. So we're still adding the inverse tangent. The minus sign is within our input of the inverse tangent. So that's square root of 2 square root of tan x, and that's minus 1. And then one thing we need to remember, after all that work, don't mess it all up and forget the plus c. So now let's get a plus c on the side there. Nice big bold letters so we can see it. And that is this here, integral of square root of cotangent x. This is our answer here. So I'm going to put that in a box for us all to see. That is the answer here. So log of tangent x plus root 2 tan x plus 1, absolute value, minus the log of tan x minus root 2 tan x plus 1, all over 2 root 2. And then add on to that the inverse tangent, or arctangent if you like, root 2 tan x plus 1, plus the inverse tangent or arctangent, root 2 tan x minus 1, all over root 2, and then everything at the end, plus a constant, plus c. Okay.